What did we do before the break? We talked about differentiation. We talked about what the derivative is. And what I want to do now is tell you about a theorem that basically is the big workhorse in terms of proving anything, and proving lots of things about derivatives. And that's something called the mean value theorem. So the mean value theorem is something that some of you have encountered it in your calculus courses. And I'm not sure that in those courses you got a sense of why we love and care so much about the mean value theorem. So let me first say what it is. So it says if f is continuous on, let's say, some closed interval and differentiable on the open interval AB, then the claim is there exists some point C inside AB such that the following is true, such that f of B minus f of A actually is equal to B minus A times f prime at this mysterious point C that we claim exists. Okay, this is the mean value theorem. Let me point out to you that this particular equation, which if you don't mind I'll call Smiley, one way to think about what Smiley is saying is the following. If you have a function and it is, let's say, looks something like this, what we're saying is if you have a point A and a point B and the function is defined on AB and it's differentiable everywhere inside, well, look what happens if I divide f of B minus f of A over B minus A, if I move this over. Don't you agree that what I get then is the slope of the secant line? And what we're saying is this slope of the secant line, f of B minus f of A over B minus A, is actually equal to the what? Yeah, do you see a point in between that has the same slope? Instantaneous slope? Might be right here, for instance. Okay. So what it's saying is there's a point in between that has the same slope as the secant line does between these endpoints. That's another way to think about what this theorem is saying. So what's the big deal? Yes, question. Well, I mean, it's certainly true if you close this interval, but this is the weakest conditions that you need. You don't need it the limits to actually the limit of the quotient of the derivative limit to exist at the endpoints. We're just, I mean, it could be one of these crazy functions where it doesn't have an endpoint limit. The derivative doesn't exist at the endpoint, but it exists everywhere inside. Okay. Think some weird sine 1 over x function that does something weird as you get close to the endpoint. Okay. So let's see. What's the big deal with this theorem? Well, here's the big deal. Okay. This is really the only theorem we have that connects the value of the function to the value of the derivative, okay, without involving limits. Okay, so notice that what Smiley does, it connects the value of f to the value of f prime somewhere, right? Without using limits. I mean, obviously the definition connects the values, but that's what's nice about this. So anytime you have a statement which kind of feels like, okay, you know, there's a lot of places in calculus where you prove things in a hand-wavy way. Well, if you want to make hand-wavy precise, you go back to the mean value theorem. So let me give you some examples here. Here's a sample application. Well, suppose you have a function whose derivative is bigger than 0 for all x in AB. What can you conclude in a hand-wavy sort of way if the slope is bigger than 0 between A and B? Then show, let's suppose this is our problem, show that f of b, what's the relationship between f of b and f of a? One has to be bigger, right? The one that's going that way, yes? Oh, well, here's a very easy proof. Actually, you can even say more, right? You can say this thing's strictly increasing, right? Why? Well, here I have some statement about the derivative, and here I have some statement about the values of the function. Well, let's see. And I don't want to go back to using limits. Oh, look, here, statement about function values and derivative. Oh, interesting. Okay, so what can I say about f of b minus f of a? And what am I hoping to show is true about f of b minus f of a? Hoping to show is positive. Well, by the mean value theorem, this is b minus a. Oh, yeah, show b if, yeah, b is to the left of a. Good. Times f prime at some point in between. Do I know what point? No. Does it matter, though? No. Why? What do I know about this creature? It has to be what? Positive, because it's one of these points. That's positive. What about this? That's positive. So this is bigger than 0 as desired. This gives us the fact that f of b is bigger than f of a. Done. Okay. Very nice applications. Very easy to see is true from the mean value theorem. Okay. We'll see many more such applications, and you will definitely see some on your homework. I mean, basically, all the problems in Chapter 5 are some version of the mean value theorem, okay? But let's see why this is true. Proof. Why is the mean value theorem true? Why is this picture, does this picture suggest why this theorem is true? What am I claiming? I'm claiming that there is a point where the slopes, the limit of the secant lines on one side and the other, because the derivative exists, actually agrees with the limit of the slope of the secant line. Just to give you a non-example, think about the following picture. Suppose I had this function. Is it true that there is a point in between a and b that has the same slope as this secant line? No, what failed? Differentiability. Now, okay, so why did it fail? Well, look, on one side, the secant line slopes are less than this slope. On the other side, they're bigger than this slope, yes? Now, of course, what happened here is, if you took these secants from this point, on this side they're smaller than this slope, and on this side they're bigger than this slope, but what kind of happened in the middle? Well, they got equal, right? Okay, so how can we sort of get wrap our heads around this idea? So here's a way to go. So the first thing is, let's just look at a special case. Would you agree, let's say the following. Let's turn this picture on.